Hi guys, it's Luke and welcome to the video on Grubb's catalysts and olefin metathesis. We've got two reactions to do here. First of all, we're going to kick things off with the ring closing metathesis, and we're going to go on to the cross coupling metathesis. As you can see, there are two types of Grubb's catalyst. In this first one, it doesn't matter what Grubb's catalyst we use. In the second one, we've got to use Grubb's 2 catalysts. I think it works more strongly. I'm not 100% sure. Maybe I should have looked. I'm going to look now. Okay, so we're back. I sort of found something that corresponds to what we're after. Effectively, Grubb's 2 catalysts work for rings that are 5+, so these are more intranuclear ones. It's very tolerant to functional groups, and it works in the presence of OH, NH, CO2R, ketones, etc., but not NO2. So anyway, let's move on. Like I said, in this step we can use either, so I'm just going to replicate that as an L for the ligand, which is obviously differs between Grubb's 1 and Grubb's 2, but we can use any in this, so I'm just going to label that L. First of all, we remove the PCY3. Obviously this step here is the pre-catalyst, we just remove that, and we get LN-RU. We keep the phenol part there because that's a part that's in the catalyst. Now LN corresponds to basically L3, basically got 3 ligands there, so we've obviously got Cl, Cl and L, that's 3 ligands. That's pretty much what LN stands for. Can have more ligands around a Grubb's catalyst, I suppose. I think that could be the case, but for the cases I've seen, I've not actually seen that happen, so that's what we have there. So here you go, we've got a circular structure of sorts. Could be any sort of structure, but for this example we'll say it's 3 carbons or something, I don't know, but not a ring. But we go for a 2+2, form the cube, and then we go for a retro 2+2 which breaks the cube. Obviously part of our molecule is bound now. The first double bond's bound, but obviously this bit's still hanging off. That gives us this, and then we've got to do another retro 2+2 to close the ring now. Obviously this is our bound part here, and we formed a double bond from this curly arrow here. Do another 2+2, form a cube, and then we've got obviously the ring structure from this part here. That arrow should more be right around there, so to form a cube, so that's 1, 2, 3, 4. That forms that there, and then we do another retro, and we've got a double bond that forms there, a circle, and then we've got plus L3, like I said technically, and CH2, which forms from breaking that bond there. So that's the ring closing metathesis. If we go for a cross coupling metathesis, we have to use 2 electronically different alkenes, for example 1 electron rich, 1 electron poor. And the mechanism for Grubb's 2 is pretty much the same. We go through another 2+2, alkene 1 we start with. Apologies about the curly arrow there. That is literally just an alkene and a carbon chain for R1, which can be anything we want. Curly arrow is literally the same as last time. One goes down there, one goes up there. Form the cube again. This time we've got an R1 group instead of another double bond. This then breaks, we lose exactly what we lost last time because the double bond forms there. And then we've got, once again, Ln corresponds to L3 in this case. Doesn't really matter. But then we do another 2 + 2. This is the second ligand that comes by. This is alkene 2, obviously as labelled here. This has got an electron withdrawing group, making it electron poor, this double bond. And obviously this one over here is more rich in electrons because it doesn't have an electron withdrawing group on. So once we've done that, we've formed the ring again, and then we go for another retro 2 + 2. We then lose the same things we lost in the ring closing metathesis part, but we make a transform of the isomer, and obviously we've got the electron withdrawing group there as well. Transform because this goes on the opposite side to the electron withdrawing group, and that's why it's trans, because trans is on the opposite side, cis is on the same side. Because it's on the same side. It's a nice little one for you to remember. And as you can see, typical electron withdrawing groups used are aldehydes, ketones, esters, amides, sulfones, and halogens. If you get really stuck, or if there's something in the exam that uses a halogen, just look out for a halogen, really. That's obviously a telling sign, something that's quite good to see. If you can't see a halogen, obviously look for the others. But if you are asked to propose a cross metathesis mechanism, use a halogen because it's, obviously easier. And that's pretty much it for our Grubb's catalyst stuff. Hopefully that was enough information. It's one of the easier reactions as well. Obviously just retro 2 + 2 and a 2 + 2 reaction really. So hopefully that was enough for you guys, and I will catch you on the next video. One last thing. Obviously the PCY3 was removed here as well before we started, so there's no pre-catalyst step in this reaction, but make sure you include that in the actual mechanism itself. Thank you guys for watching. Next time we'll be going on to silanes using our silicon atoms, and there's quite a lot of reactions for that one, so it'll be quite a longer video, but there's plenty of stuff to look at. So thanks for watching, and I'll see you on the next one.